This unit of material combines a little bit of the stuff from Chapter 11 with a good bit of the stuff from Chapter 12. Chapter 11 talks about benzene and some of the special nature of its chemistry and how to name derivatives of benzene. Chapter 12 deals with the most common type of reaction that benzene and its derivatives undergo. That's the electrophilic aromatic substitution. I want to talk about benzene itself for a little bit, though. This diagram, figure 11.2 from your book, is to illustrate how benzene has a special degree of stability that's not normally found in alkenes that we might compare it to. If you think back to chapter 5 and 6 in your book, those were the two chapters where alkenes were introduced, compounds that are characterized by that carbon-carbon double bond. And benzene is oftentimes represented looking like a cyclohexane ring with 3 alternating double bonds. But it really undergoes chemical reactions that are unexpected when you compare them to simple alkenes like propene or ethene. And this diagram is a clue to its special nature. On the far left, what we're seeing here is the reaction of all of these compounds with enough hydrogen to turn them into cyclohexane. That's the molecule down at the bottom. Remember, with these kind of energy diagrams, the higher up a structure is shown, the less stable it is. And this is showing the amount of heat units in kilojoules per mole that's released when different compounds are hydrogenated. Again, that's just reacting with hydrogen. So here we have over on the left cyclohexene, and it has 120 units of energy that it gives up when it undergoes that reaction. And they show the cyclohexane down here in its typical chair conformation. Well, if you have a 6-membered ring with 2 double bonds, and if you react it with 2 molecules of hydrogen, you might expect to get double the quantity of heat energy released. And it's almost double. 231 is not exactly double 120, but it's pretty close. Well, if we continue that and add a 3rd double bond and get this molecule at the top, again, this is how benzene is oftentimes represented. But the thing is, if you react that with 3 hydrogen molecules to convert it down to cyclohexane here, it doesn't give up 3 times 120. We might expect something close to 360 as the energy give up, but no, it's only this number in the middle, 208. So benzene is therefore more stable than the cyclohexadiene, that molecule in green over here. So it's much more stable than we would expect if it were really just a plain alkene that happened to have 3 double bonds. The difference in this 208 number and what we might expect, which was 152 units higher than that, that difference is called resonance energy, and it's the amount by which benzene is stabilized. There's a number of ways you can analyze the bonding in a benzene molecule to illustrate this type of stability. Oftentimes benzene is shown as a cyclohexane ring with a circle drawn in the middle. That's a combination of the 2 resonance forms you could draw based on just having the 3 double bonds alternating. Doesn't matter which carbons have the double bond or not, as long as there's 3 of them and they're alternating. And we still use this form of benzene to represent its structure. But as we'll see, it's not easy to do things like react benzene with hydrogen molecules to get rid of those double bonds. It tends to react in ways that preserve those 3 alternating double bonds, and that just gives benzene a lot of stability. This next slide shows a molecule very similar to benzene, but this time it's not in a form of a ring. We've still got 3 alternating double bonds, but notice the ring is not closed on the right side. So this is 135 hexatriene. It gives up an amount of energy that is expected based on it behaving like a normal alkene. That's reasonably close to that 360. It's a negative number here because it's releasing that energy amount. But the point of this slide is that this is a regular alkene with regard to how it reacts with hydrogen. So benzene not only needs those alternating double bonds, it needs it to be in the form of a 6-membered ring.